Hello students, let us start our new session of chapter 10, Mechanical Properties of Fluids. Let us understand dynamic lift, which is a force acts on a body by the motion of fluid. Here three cases are defined: ball moving without spin, ball moving with spin, and aerofoil or lift on aircraft wing. Basically, while the spinning ball deviates from parabolic trajectory path through the air, we can explain the concept based on Bernoulli's principle again. So, ball while moving without spin, in diagram A, that is the streamline is shown. Here, as you can see, the symmetry streamlines are there, which defines the velocity of air above and below the air is the same, which generates a zero pressure difference, and the air exerts no upward or downward force onto the ball. Second case in which the ball moving with spin. So here ball while spinning, it drags the air along it. So here, if the surface of the ball is rough, then more air can be dragged. Here, streamline of the air for a ball is shown for the spinning ball. So the ball is moving at forward direction. With the air, it moves backward. So ball is moving in forward direction. With that, air is moving backward direction, and the velocity of air above the ball is larger and below the ball it is smaller. So here, based on that, the streamlines above the ball is crowded and below the ball it is rarefied. So this generates a difference in velocities of air, which generates the pressure difference between upper and lower faces of the ball, which gives you the upward force on the ball. So this is what the dynamic lift is generated due to spinning of the ball, which is known as Magnus effect. In third case, it defines for the aerofoil, which shows that while the solid piece shaped to provide the upward dynamic lift, it moves horizontally through the air. So cross section of the wing of aeroplane, it's look like the aerofoil with a streamline around it. When the aerofoil moves against the wind, the orientation of the wing relative to flow of direction, which generates the streamline crowded together above the wing than the streamlines below it. So the flow of speed onto the top is higher than the below side. So which generates the upward force in a dynamic lift of the wing, which balance the weight of the plane. Right? Let us understand the example regarding the same. A fully loaded Boeing aircraft has a mass of 3.3 into 10 raised to 5 kilogram. Its total wing area is 500 meters square. It is in level flight with a speed of 960 km per hour. Estimate the pressure difference between the lower and upper surface of the wings. Next, estimate the fractional increase in the speed of the air on upper surface of the wing relative to the lower surface. Its density of air is given 1.2 kilogram per meter cube. So here we need to determine pressure difference between the lower and upper surfaces of the wing. For that, pressure difference delta P into A, which generates the force. So weight of Boeing aircraft is balanced by the upward force due to the pressure difference delta P. So generated force F equal to delta P into A, and the force is given. Force would be equal to mg. M is given, mass of the aircraft 3.3 into 10 raised to 5 kilogram. G is taken 9.8. So F equal to M into G and F equal to P into A. By equating both the equation, we are having delta P into A equal to mg. So delta P equal to mg by A. Substitute all the values and pressure difference we are having 6.5 into 10 raised to 3 Newton per meter square. Now, the next thing we need to calculate, that is a change in speed of the air. So here, the height difference between the top and the bottom side can be ignored. So pressure difference delta P equals to, based on the kinetic energy variation, 1/2 rho V, 1/2 rho V2 square minus V1 square. V2 is the speed of air at upper surface and V1 is the speed under the bottom surface. So V2 minus V1 equal to twice delta P divided by rho V2 plus V1. Here V2 square minus V1 square would be equal to V2 minus V1 into V2 plus V1. And make the subject of formula V2 minus V1. And take the average speed, that would be V2 plus V1 by 2. And that average speed is given that 960 km per hour. So here average speed is V2 plus V1 by 2, that is 960 km per hour. Can convert into the meter per second, that would be 267 meter per second. So V2 minus V1 divided by V average equal to delta P by rho V average square, nearly equal to 0.08. So here the speed above the wing, that needs only 8% higher than the below the wing. Clear? Now the next topic, viscosity. Here the fluids offer some resistance to motion. This force exists where there is a relative motion between layers of the liquid takes place. This resistance of the fluid is like internal friction. Internal friction existed when solid moves onto the surface. That is known as viscosity. Let us understand it through the diagram. As you can see into the diagram A, for example, oil enclosed between two glass plates over here, as you can see in the diagram A. The bottom plate is fixed and the top plate is moving with the velocity v. If the oil is replaced by honey, then greater force is required to move that plate with same velocity, because honey is more viscous than oil. The fluid in contact with the surface has the same velocity as surface. So the layer of liquid in contact with the surface moves with the velocity v, and the layer of fluid in contact with the fixed surface at bottom surface, it's stationary. So here the layers, velocity of the layers increases from bottom to top. At bottom the velocity is 0 and at top let us consider velocity is v. So for a layer of liquid, upper layer pulls at forward side while the lower layer pulls it backward side. This generates a force between the layers. This type of flow is known as laminar. Now, as you can see in the diagram B, while the fluid is passing through the pipe or tube, then velocity of liquid along the axis is maximum and it is decreases gradually towards the surface and it goes to 0. So here the velocity on a cylinder surface in a tube is constant. So here in diagram A, you can see that the portion of liquid having initial shape A, B, C, D. Now as upper surface will move, so now after interval of delta T, the fluid takes a shape A, E, F, D. So during this time interval of delta T, liquid undergoes through a shear strain. And shear strain is delta X by L. This strain is in a flowing fluid increases continuously. So here the stress is found experimentally, which depends on a rate of change of strain or strain rate, that is delta X by L into delta T, that is V by L, because distance per time is velocity, so that is V by L, that is strain. So here the coefficient of viscosity is denoted as eta, that is defined as a ratio of shearing stress to the strain. So stress is F by A and strain is V by L. So eta equal to F by A divided by V by L equal to FL by VA. That is coefficient of viscosity eta. Its SI unit is PI Poisson. And other unit can be defined as Newton into second per meter square or Pascal into second. It's a dimension m, L raised to minus 1, T raised to minus 1. Here one table is given which gives the viscosities of fluid. By this comparison, we can see that blood is thicker or more viscous than water. So its relative viscosity is eta divided by eta of water. So blood remains constant between 0 degrees Celsius to 37 degrees Celsius. The viscosity of liquid decreases with temperature and increases in case of gases. Again, go through the example. A metal block of area 0.10 meters square is connected to a 0.01 kilogram mass via a string that passes over an ideal pulley, considered massless and frictionless, as we can see in the diagram. A liquid with a film thickness of 0.3 millimeter is placed between the block and the table. When released, the block moves to the right with a constant speed of 0.085 meter per second. Find the coefficient of viscosity of the fluid. So here, while we want to determine the coefficient of viscosity, we need to determine first stress and strain, because that is the ratio of stress to strain. So here, a metal block is moving to the right because of the tension in the string and the tension T, that is equal to mg, and m is given 0.01 kilogram and g 9.8 meter per second square. So force or tension on the string, that is 9.8 into 10 raised to minus 2 Newton. So stress is F by A, 9.8 into 10 raised to minus 2 divided by A, 0.1. And strain, that is V by L, velocity by length, and velocity is given 0.085 meter per second and its thickness is given 0.03. So here by equating all, the thickness is given 0.3 millimeter. By equating all the values of F, A, V and L, we able to get coefficient of viscosity eta equal to F into L divided by V into A. And eta we are having 3.45 into 10 raised to minus 3 Pascal into second. Clear? Here we are going to end the session. Hope you understood. Thank you.